Now there are two families of elements where the expected configuration of electrons is not the one observed by experiment. Actually, there are more sporadic examples, but these are the only ones that you need to know about. The expected configuration for the elements chromium and copper are shown here. Their actual configurations result from taking the expected configuration and moving one electron from the 4s orbital and adding it to the 3d orbital. This discrepancy is due to the fact that the expected configurations have partially filled 3d subshells, but having a full or exactly half-full 3d subshell, like we have in copper and chromium respectively, is more energetically favorable than just an arbitrarily partially full 3d subshell. This trend in the outermost s and d electrons applies to the element directly beneath chromium, which is molybdenum, and it also applies to both of the elements directly beneath copper, which are silver, and then one place below that, gold. This diagram of the periodic table is color-coded based on the subshell where the last electron in an element's electron configuration is placed, and at this point you can probably see where the shape of the periodic table comes from. It's not arbitrary at all. It groups elements along lines of electron configuration, which also happens to line up with similar chemical and physical properties in many cases. Helium is the only element somewhat out of place, and it's usually placed above the other noble gases due to its shared chemical and physical properties. An alternative way of determining the correct orbital ordering, besides the arrow diagram from before, is to use this trend. The drawback of this method is that you need to remember that within each row, the d subshells are offset from one another by their row number, and the f subshells are offset by 2 from their row number. Still, some people prefer this method, which is fine if it works for you. While we've gone over the rules to place the full set of electrons for any atom, it's important to know, especially in the next few chapters, that it's really only the outermost electrons that have a major impact on an element's chemical and physical properties. These are known as the valence electrons of an atom, and for main group elements, the column number corresponds to the total number of valence electrons. So group 1 elements have 1 valence electron, group 2 have 2 valence electrons, the halogens in group 7, if you use the older system, have 7 valence electrons, etc. If you take the electron configuration of an element in noble gas shorthand, the number of valence electrons is given by the number of electrons that show up after the noble gas chemical symbol. There is an exception, though. Any d or f electrons do not count if the d or f orbitals are completely filled. For instance, the configuration for bromine is argon 4s2 3d10 4p5, but we don't count the 3d electrons because they belong to a full subshell. Finally, let's discuss something we'll look at a lot more in the next chapter, which is periodic trends. Specifically, the trend in the sizes of atoms based on their position in the periodic table. We're really only going to focus on main group elements for these purposes. The trend in size within any column of the periodic table makes enough sense. As you go down any column, the number of electrons increases as the atomic number increases, and the outermost electrons belong to subshells with higher principal quantum numbers. As a result, the outermost electrons are further from the nucleus on average, and hence the atom itself is effectively larger. Because atoms have spherical electron clouds overall, we use atomic radius as a proxy for atomic size generally. The trend across rows is a bit more complex to rationalize. Somewhat counterintuitively, as we go from left to right across the periodic table, the atomic number and number of electrons increases, but the atomic radius will tend to decrease. To explain this, we need to invoke the concept of effective nuclear charge again. As the atomic number, and hence the number of protons, increases across a row of the periodic table, so does the effective nuclear charge. As a result, the electrons are more strongly attracted to the nucleus, and hence held closer to it. This results in a smaller atomic size due to the electrons not being as far away from the nucleus. And with that, that brings us to the end of Chapter 5. Thank you for listening, and I hope you continue to stay safe.